Cool. Okay, so let's continue. Did we have homework today? 5.7?
Yeah.
Are there any questions? Okay. What's 43?
It was just
Show
That the derivative of arctan x. And then in parentheses you have 10.
It's arctan of tangent.
arctan
Of tangent.
of tangent x.
Tangent.
Oh, tang. Oh,
Equals the hyperbolic secant to x.
done? So I'd just start by trying to find the derivative here. Okay, so what's the rule for arctan? Derivative of arctan of u. I probably asked that on the quiz. Is u prime over 1 plus u squared, right? So we're going to have 1 plus u squared, which is in this case tang squared. And the top is the derivative of tang, which is what?
Hyperbolic sequences.
Secant squared.
Hyperbolic secant squared, right? And now basically what we want to do is we want to be able to simplify this to get that guy. Okay, so how do we do that? Ideas, what can
Write
you...
it in terms of cosine and sine.
Come again?
Rewrite it in terms of sine and cosine.
Right, one of the easiest ways to rewrite in terms of sinh and cosh, because those identities are easy to work with, so we can do that. So secant hyperbolic is...
1 over cosh squared x.
Huh?
1 over cosh squared x.
1 over cosh squared, 1 plus
Sin squared x over cosh squared x.
sinh squared over cosh squared. Okay, that's an option. What else can we do?
you can turn the sig squared into 1 minus tang squared on top, like, just so it's tang over tang. 1 up. Yeah, there.
Yep, what do you want to do?
You use the identity, just turn that into tang, so you don't have to deal with the
Turn what into tang?
the sec squared into
Yeah.
1 minus tang squared x.
You could also do that. This wouldn't be that though, but you could do that. I'd have probably done that, but what is, if we wanted to go here, what can we say about this?
And we get 1 over cosh squared x plus sin squared x.
Right, this is a complex fraction. The LCD is cosh squared. I can multiply top and bottom by cosh. So I would get 1 over cosh squared x plus sinh squared x.
And then double angle from there. It's like the denominator is cosh 2x.
Right, there's a double angle formula. This denominator is cosh 2x. How do we know that that's cosh 2x?
Isn't it the identity from the triangle formula?
Is that given directly as an identity in the text? Or it is something you can figure out though. Right, so for example, there are tons of ways you can actually figure this out. Remember that cosh squared boom. Cosh squared would be what? Oh, sorry, cosh 2x
Cosh x.
is just what?
Cosh squared x is sin squared.
E to the 2x plus e to the minus 2x over 2. How do you know that's this guy? How'd you get from here to that? Come again?
to the 2x is the same thing as e to the x squared.
That's correct. And then what would you do with that? So I can write this as e to the x squared and that as e to the minus x squared. So I have the sum of squares. What can I do with that? Come again? This would be what? Okay, he said that, so this is e to the minus x squared. Okay, what do we do with that? I mean, there are nicer ways to get to it. We already have an identity with cosh and sinh, right? So you could even use that. That's not the same thing. Maybe you guys are having trouble going backwards. What would cosh squared x look like? That's just e to the x plus e to the minus x all over 2 all squared, right? This is e to the 2x plus 2 plus e to the minus 2x all over 4, right? And if I look at sinh, this is just e to the x minus e to the minus x over 2 squared, which gives me e to the 2x minus 2 plus e to the minus 2x all over 4. And of course, then if I add these two, cosh squared x plus sinh squared, I would end up with e to the 2x plus 2 plus e to the minus 2x plus e to the 2x minus 2 plus e to the minus 2x all over 4. This will give me 2 e to the 2x plus e to the minus 2x all over 4. This will cancel that. So this gives me e to the 2x plus e to the minus 2x all over 2, which by definition is cosh 2x, right? So this you can jump to this, and that's just secant hyperbolic of 2x. And there are several ways you could have done this. Again, you could have done this as 1 minus tang, and then you get to this by another route, but it's like those trig identities from, from pre-calc. There are tons of ways usually you can actually get to one. So you just pick your poison and move with it. Other questions?
55.
Huh? 55, what does that say?
Integral sinh root x
Integral of sinh
radical x divided by radical x.
divided by?
Radical x. Yes.
Who knows what to do here? Right, u substitution, u equals radical x. Du would be 1 over 2 radical x dx. And so 2 du would be 1 over radical x dx. And so the integral you get is 2 times the integral of sinh u du. Integral of sinh is just cosh. And then you just replace the u. So this is 2 cosh radical x plus c. So the trick is the radical x was your u, right? That's what's make things complicated, and its derivative is somewhere else in the function. Other questions? No? 47. What does it say?
It's a graph. I mean, it's a diagram.
Oh, yeah.
Okay. Okay, a telephone line hangs between two poles 14 meters apart, blah, blah, blah. Okay, so they actually put it on an axis for us. So this goes to 7, that goes to -7. There's a telephone line hanging between these. They mentioned for us that this meets at an angle theta. And the height seems to be 5. That's your y-axis, that's your x-axis. Okay. And so it says the telephone line hangs between two poles 14 meters apart in the shape of a catenary. So that's the equation of this function here. This is f of x or y equals 20 cosh x over 20 minus 15. Where x and y are measured in meters. Okay, blah, blah, blah. Part A, find the slope. Find the slope of this curve where it meets the right pole. So we want to find the slope here. Okay, how do we do that? Find the derivative, right? So we know that y is equal to 20 cosh x over 20 minus 15. This means that y prime is equal to derivative of cosh, the sinh, x over 20. Chain rule says we have to multiply that by 1 over 20, which is going to cancel this 20 here. Derivative of 15 is 0, so that's your y prime. So this means at the point of connection, slope is just going to plug in 7. Right? So this is just y prime at 7, which is sinh of 7 over 20. So that was part A, that's the slope, sinh of 7 over 20. B, find the angle theta. So basically I know I sort of know what's going on here. So now I know theta is this angle, and I know the slope of this guy is y prime equals sinh of 7 over 20. Okay, so how do I find theta?
Like the inverse of the slope is like, so 1 over tan theta is sinh 7.
1 over tan theta equals sinh? What do you mean?
Because
Like I can draw this, I can create a right triangle here,
yeah,
right? And if the slope, and remember slope is equal to rise over run, right? Now that I actually know is equal to sinh of 7 over 20. So I can just think of that as 7 over 20 over 1, right? So then I know the height of this, I can call it sinh, 7 over 20, let the run be 1. And then I can just use trig. I know that tangent of theta is opposite over adjacent, sinh 7 over 20. Which if I wanted, I could call that cosecant h 7 over 20, which means that my theta is just going to be tangent inverse of this guy. which if we don't have a calculator, that's sort of where you do it. Okay. Other questions? Huh?
Okay.
Yeah. Who was this? Other questions? No? I guess you can pass the homeworks up. So let's see here. So because of the religious holidays last week, this one time only I'm accepting late homework. So for those of you who had to be absent due to the religious holidays, then you can hand me the homeworks from 5.5 up to 5.7. You have up until tomorrow. So you can give me those homeworks if you want to. Again, the test is next Tuesday. The review problems are already on my website. So you go to my website and you'll see test 1 review problems, and you'll see problems that you should review for the test. So you can check those out. And for now, we're going to continue with 5.8, which is the last topic that's on the test. The main thing that we did here was L'Hopital's rule, if I recall. Indefinite forms and L'Hopital's rule. So let's pick up where we left off. So L'Hopital's rule is the real star of this section, and we did a few topics. We did a few forms. So we looked at the form 0 times infinity. That's when we actually computed the limit as x approaches 0 plus of x ln x. Right. So this looked like 0 times infinity. Well, it was like a negative infinity, but the sign doesn't matter. And so how did we do this? You rewrote this, right? This is ln over 1 over x, right? And why did we do that? Well, because we want to be able to use L'Hopital's rule, which has to have a special form. So we have to remember that we can only apply L'Hopital's rule if we look like infinity over infinity or 0 over 0. And so we rewrite it that way. And so now we can apply L'Hopital's rule. And L'Hopital's rule says, what does the rule say? Right. If you have a limit going to infinity over infinity or 0 over 0, then that limit is equal to the limit you get if you just differentiate the top and differentiate the bottom. So I can differentiate this, get 1 over x, then this one get minus 1 over x squared, and ultimately the answer was 0. We then looked at the form infinity over infinity, which means it looks exactly like the form that L'Hopital's rule works in. We looked at something like x goes to infinity of ln x over x, which this looked like infinity over infinity. So we could apply L'Hopital's rule right away. Derivative of ln x is 1 over x, derivative of x is just 1, and as x goes to infinity, that is again 0. And we use this to illustrate the fact that polynomials grow a lot faster than logs, and we reminded ourselves of that. I then gave, we actually did another example here, limit as x approaches infinity of e to the x over x. This went to infinity over infinity. We applied L'Hopital's rule, which means I could differentiate the top, which is e to the x, differentiate the bottom, which is 1. That went to infinity. We use this to illustrate that exponentials grow a lot faster than polynomials. So I believe we did all these examples last time, so I'm just quickly recapping just to remind you of where we were. Then I looked at the form infinity minus infinity, which is another indeterminate form. And the example there was the limit as x approaches infinity, something like e to the x minus x. And the trick here, it's not in L'Hopital's rule form, but we could actually do something like factor out an x, where I know this is going to infinity. This guy here is also going to infinity by what we did previously. Infinity minus 1 is still infinity, so really what I have is infinity times infinity. And so that is infinity, right? So infinity times infinity is not an indeterminate form. So usually if you have a subtraction, what you're going to try to do is factor things to get into a nicer form that you can determine. Okay. Did I do ln x minus x?
Yeah.
Right, we did the other example, x approaches infinity of ln x minus x. Again, this approach infinity minus infinity. The trick again here, you don't need L'Hopital's rule. All you did was factor out an x. This gives you ln x over x minus 1. This guy would approach infinity. That guy would approach 0. Right. That guy would approach 0, and so we would have essentially infinity times minus 1, because there's a minus 1 here. So the answer there was negative infinity. Was that the last example I did? Or was it? I did e to the x minus x. I did ln x minus x. That was the last one, right? Okay, let's do some more examples. So the important thing to take away, L'Hopital's rule, it only works if you have 0 over 0 or infinity over infinity. Right? That's the only time you can use it. That's the important thing you have to remember. So if you're not in that form, you somehow use algebra to rewrite it to look like that form, or use algebra to sort of factor things to make things easier for yourself. But you can only apply L'Hopital's when you're in that form. So that's the important part. Let's look at something like limit as x approaches negative infinity e to the x times x squared. Now, what is this approaching? As x approaches negative infinity, what happens to e to the x?
0.
It goes to 0. And as x approaches infinity, negative infinity, what happens to x squared? It goes to infinity. So this is a 0 times infinity thing. So we can't apply L'Hopital's. Can we rewrite it so that we can apply L'Hopital's?
E to the x over 1 to the x. E to the x over 1 over x squared.
Is that how you'd rewrite it? You do get 0 over 0 now, yeah, but is that okay? That's actually a bad idea. Does anyone see why?
You differentiate 1 over x squared.
Differentiate 1 over x squared, you're going to get what? Minus 2 over x cubed, right? You're going to end up in a worse position than you started. Now you're not with a squared x, you're with a cubed x. It's not going to help you to apply L'Hopital's here. What's another option?
Just put a 1 x. Just you put a 1 x.
Put the what?
Only 1 power x. And then leave 1 x using the top.
So you put one x here and leave an x here. But then, don't you sort of end up in the same situation in the top that you had before? In the top it's now a 0. It's now a 0 times infinity.
Could you rewrite it as the limit as x approaches infinity of e to the negative infinity times negative x squared?
What do you mean? Tell me how you'd write it.
So like the limit statement would be as x approaches infinity, and then you would negate all the x's.
You could. You don't have to. Making it needlessly complicated.
I mean, because then you would have e to the negative x, and then you could write that as like negative x squared over e to the x.
Why don't I just do that now? X squared over e to the minus x. Right? If bringing the x onto the bottom cause trouble, bring the other guy onto the bottom. Right? This approach is what now? Infinity over, if I plug in negative infinity here, negative times a negative infinity gives me positive infinity, which gives me e to the infinity. So that also gives me infinity. I get infinity over infinity now. I can apply L'Hopital's rule. So let's do that. This would be equal to, what's this? Derivative? 2x, derivative on the bottom? Negative e to the minus x. Okay, what's the limit now? It still goes to infinity in the top. What happens in the bottom? It still goes to a negative infinity.
You still derive that. You still do the derivative of that. So it will be 2 over negative.
Apply L'Hopital's again. There's nothing that says you can only apply it once, right? In fact, this section I didn't want to give it away. I have titled in my notes, repeated L'Hopital's rule. You can apply it as many times as you have to. As long as you have a form infinity or 0 over 0, you can keep applying L'Hopital's rule, right? So I did here, got the form infinity over infinity, apply L'Hopital's rule. I still end up in the situation infinity over infinity, apply it again. I can see here though, that eventually it's going to stop because I had an x squared, now I'm getting to an x. I can see things getting better. The other way around, when I put the x in the bottom, things were getting worse. Right? The powers seemed to increase in some sense, and that was making things worse. But putting it in this way, my powers started to break down. And so I can just keep doing L'Hopital's rule until things get nicer. So now I differentiate the top, I get 2. Differentiate the bottom, I get e to the minus x. So this is 2 over, this is a negative infinity. So now this is 2 over, which is? So that limit is 0. Okay. So don't be scared, you can actually apply L'Hopital's more than once. As long as you have infinity or 0 over 0, you keep applying it, right? A word of caution here, because I don't want people to go crazy, because I've seen this happen before. After applying L'Hopital's once, it's to your benefit to actually simplify before figuring out if you have to do it again, right? Because there are some times when you do it once and you can simplify and you don't need to do it again. Whereas, you know, you might get the form infinity or infinity, but you really don't need it. You just simplify and it'll work out. In this case, though, simplifying wouldn't help. I would still end up in the same sort of situation, so I can apply L'Hopital again. But after every step, you're going to want to see if you can simplify, and that might actually make your life easier. Let's do another example. Limit as x approaches 1 from the right side, 1 over ln x minus 1 over x minus 1. What is this approach? As x approaches 1 from the right side, what happens to this? ln will approach 0, but will it be slightly positive, slightly negative? Slightly positive, right? Don't forget your graph. ln looks like this. If you're approaching 1, you're slightly bigger than 0. So this guy goes to a positive infinity, right? Minus, if I approach 1 from the right side here, means my x is a little bigger than 1. So x is like 1.00000001, right? I still approach 0 in the denominator, but slightly positive again, right? So this becomes infinity minus infinity form. So now we're going to have to try something to get this to work out. What do you think? Give me some ideas. Huh? To do what? Cross multiply isn't the exactly the correct phrase you want. You want to combine the fractions. Right, so let's actually do that. There's a trick to combining fractions really quickly that looks like cross multiplication, but technically it's not. You can multiply this denominator across that, you get x minus 1. Multiply this across that, you get minus ln x. And then you can multiply each denominators individually. So this gives you x minus 1 times ln x. What's this going to now? X is approaching 1, right? So 1 minus 1 is just 0. X is approaching 1 here from the right. That guy is going to go to 0. So this looks like 0 divided by, x is approaching 1.
0 over 0.
And as x is approaching 1 here, I just get times 0, right? So it's 0 over 0. I can apply L'Hopital's then. What happens? You get 1 minus 1 over x divided by product rule, ln x plus x minus 1 over x. Looks like what happens now? So you actually get 0, like if I plug in 1 here, I get 1 minus 1 on the top, that's 0 over 0 again, right? Do I automatically apply L'Hopital's rule? Well, I'm not really looking forward to differentiating things like that. So I can simplify, right? Multiply by x over x, which is the LCD. So this now becomes the limit as x approaches 1 of x minus 1 over x ln x plus x minus 1. Right? So that looks a lot nicer, right? So do we still need L'Hopital's? Right, it still goes to 0 over 0. Right? So darn it. Try to simplify, didn't really help us. Let's keep moving. We can apply L'Hopital's again, because of course we're in the repeated L'Hopital's rule section. So now derivative of the top is 1. Derivative of the bottom, ln x plus 1 plus 1. Right? Now, as x goes to 1, ln x goes to 0. Log of 1 is 0. So I end up with what? This is a half. That crazy thing, actually, the limit is a half. So again, just show you, don't be afraid to apply L'Hopital's more than once. You might have to do it 2 or 3 times. After every time, try to simplify though, it'll make your life a lot easier. But you can do it several times. Any questions so far? But again, at any given time, you have to have either 0 over 0 or infinity over infinity, or you can't apply it. If you don't have that, you have to rewrite it. Here I had 2 fractions subtracting. Combining the fractions was a way to get one big fraction. It was a way to help myself out. So let's make things a little bit harder because it's too easy so far. Using logs and exponentials. To help with L'Hopital's rule. So when we were differentiating, do you guys remember when it was convenient to use something like log differentiation? Huh? when would you use a log differentiation?
When
Huh?
there are so many product or
That's one when the product, and it'll be horrible using the product rule or the quotient rule. What else? There was another case where you use logs.
And the function is in exponential.
When the exponent is a variable, right? That's one of the reasons. So let's look at examples here. What if I ask you to find the limit as x approaches, what did I have here? 0 from the right of sine x raised to the xth power. Now this approaches 0 to the 0, which is an indeterminate form, right? On top of that, I have an x in the power, right? See here, power is a variable. Think logs can help. Right? This is usually when you're going to want to use logs, because logs turn powers into products. Right? So let's actually see how this can work. I'll show you two ways. One way using the log, and then one way is using an exponential, and then you can sort of choose which one you like more, and use that one all the time. I don't particularly care. Okay, so let's call this something. Let y be this limit. What I can do is here, ln both sides. Now back in Calc 2, I believe, well, no, even Calc 1. In Calc 1, we learned that for continuous functions, we can take factor limits out, right? So this is the same as the limit as x approaches 0 of ln of sine x to the x, right? Because that's what continuity means. Continuity means, remember, limit as x approaches a of f of x equals f of the limit as x approaches a of x equals f of a, right? That was the definition of continuity. Okay, ln is a continuous function, which means this limit I can move it on the outside, and that's why this can work. And now when I look at this function, I can actually transform that into x times ln of sine x. Right? So now this is the limit I have to worry about. Before I had sine x to the x, which was 0 to the 0, that was a problem. But now by logging both sides, I end up having to deal with this limit. What does this limit approach? This goes to 0 times negative infinity. 0 times infinity is no good. What can be done? If I raise to the e, I just go back to the original situation. It won't help. Forget all of this. Pretend that this was the question. How would you approach it? Why would you do a product rule? Differentiating here would be illegal. It's not the right form. Huh? Right, you rewrite it. ln of sine x divided by 1 over x. Don't forget the lessons we just learned a few minutes ago. You have to rewrite it to be in a nice form. This would approach what? Infinity over infinity. Well, technically negative infinity over infinity, but it doesn't matter. Which means I can apply Logarithms. Derivative of this is cosine x over sine x. Derivative of this minus 1 over x squared equals. So this is the same as limit. Again, I'd simplify first before I do anything else. This is just minus x squared cosine over sine x. That's still 0 over 0. Can I do anything about that though? Huh? You don't need L'Hopital's again. Hmm? I could write cotangent, it wouldn't make much of a difference though. It's actually better to leave it in this way. Remember those special trig limits? No, we talked about them last time. X over sine x. I can rewrite this guy as x over sine x times x cosine x. What's x over sine x approach as x approaches 0? This guy approaches 1. As x approaches 0, what happens to this guy?
0.
That guy approaches 0. This is actually just minus 1 times 0. Right? Doing L'Hopital's rule again, I'll have to do like product rule or remember the derivative of a cotangent. Like, don't want to do that. Are we done? What's wrong? Don't forget. Right? This is why I'm going to show you the other way, because I know students often forget that they log both sides in the beginning. Right? So this means ln of y gave us 0. So what is y? Y has to be 1, right? Raise both sides to the e. So the limit is actually 1. Right? Don't forget that you log both sides in the beginning, right? So sometimes it might take a long time, but make sure you remember. Or, so that you never forget, you can use the exponential in the first place. Use exponentials. Can anyone guess what identity I'm going to use? E to the ln of x is just x, right? This works in general. So if there's an f of x here, there's just f of x here. So if I have this, what was the original? Sine x raised to the x. I can rewrite this as e to the ln of sine x to the x. Right? And now I just do the problem with this. So with the big E here, I'll never forget that I have to raise both sides of the E at the end, right? Because now I'm carrying that E with me the whole time. It's going to be right there in my face, right? So then what we're going to do is, in the power now, you can bring this guy down. So this is just a limit as x approaches 0 plus of E to the x ln sine x. And then exactly the same thing that we did here, we're going to do here, but now all the action is happening in the power. So at the end of the day, I'm going to get this guy going to 0 in the same way. So I'll get the limit, well, so at the end of the day, I'll get e to the 0 by doing all of that, which is going to be 1, right? So I can use the exponential here, and so I'll never forget to exponentiate at the end. So that's one idea, using this identity. These are very important identities to use. So whenever your power is a variable, you can think of using logs, or you can think of using the exponential like this, if you're one who you think you'd forget, right? It's up to you. It's a personal preference. There's no difference between the two, actually. Let's do another example. Try to get things to sink in. Let's make it a little easier, but the same kind of process. X to the x. How would we do that? Who wants to do the log both sides thing?
E to the ln.
No one likes that method? Everyone prefers e to the ln? Okay. So I can write this as e to the ln of x to the x, which just becomes e to the x ln x. Right? So in the power, what's going on? If I'm taking this limit. I get 0 times negative infinity, right? I have a 0 times infinity happening in the power. Useless to me, right? So what am I going to do? You can write this as something like ln x over 1 over x. And now I have infinity over infinity in the power. Which means now I can apply L'Hopital's rule. Let's do it over here. Which means now I can apply L'Hopital's rule. So this is going to be the limit as x approaches 0 from the positive side of e to the differentiate ln x, I get 1 over x. Differentiate 1 over x, I get minus 1 over x squared. Simplifying that, I would have e to the minus x. Now I can let x go to 0. This just gives me e to the 0. The limit is again 1. Questions? Your brains are fried from the quiz, huh? Like, oh my god. Anyway, tons of problems like these to do in the homework. Once you get into the group, it'll actually be a lot easier than you think. So these were both formed 0 to the 0. We can also talk about the form 1 to infinity, which is, I'm going to show a very important thing. We're going to find the limit as x approaches infinity of 1 plus 1 over x to the x. What does that equal? Like the final answer. This is actually e. Remember, like 3 sections ago, I defined e to be a limit, and I'm saying, oh, eventually I'll prove it to you. Well, now we're going to see that that's actually e. Yay, I'm so excited. Okay, so let's pretend we didn't remember that, but we should. That was e. That this is e. We should remember this. How do we actually do it? There's a variable in the power, so I'm going to think of either logging both sides or write things as e to the ln of 1 plus 1 over x to the x, which is just the limit as x goes to infinity of e to the x ln 1 plus 1 over x. This, by the way, would go to infinity times, here if x goes to infinity, 1 over x goes to 0, so this goes to ln of 1. So this is infinity times 0, useless. So we're going to rewrite it. So this is equal to the limit as x approaches infinity of e to the ln of 1 plus 1 over x over 1 over x. This guy now goes to 0 over 0. So I can apply L'Hopital's rule in the power. Again, we can do this because the exponential is a continuous function. I can just take the limit and pass it through the function. So L'Hopital's in the power gives me, derivative of this is 1 over 1 plus 1 over x times the derivative of 1 plus 1 over x, which is minus 1 over x squared, divided by derivative of 1 over x is minus 1 over x squared. this cancels that. So I have the limit as x approaches infinity of e to the 1 over 1 plus 1 over x. Now as x goes to infinity, this guy goes to 0, and I just end up with 1 over 1. So I just end up with e to the 1. So that limit is actually equal to e. Prove it. Okay. That's it for that section. Especially lately, it's actually a very typical problem here, which you'll see from practicing the review problems. To put problems in the final where you're finding a limit where there's a variable in the power. So you're going to want to know this technique really well. Like I said, doing the homework and practicing the review problems. After going through it a few times when your minds are more fresh, it will be nothing to worry about. Let's introduce 6.1. Yes. This is 1 over x here. So as that x goes to infinity, that goes to 0. So this goes to ln of 1. ln of 1 is 0. And as x goes to infinity, this goes to 0. So I get 0 over 0. Which means I can apply L'Hopital's rule and end up with 0.
Are we doing 6.1 tomorrow or do
Well, we don't have class tomorrow.
Thursday?
I'm not going to devote a whole class to review, but if you do the review problems and you have questions, you can ask me a couple of them in the beginning, sure. But I want to show you something cool. This is called integration by parts. So chapter 6 is all about integration. It is a very fun chapter, where we're going to learn about all sorts of interesting things. This is where you realize that integration is a beast when compared to differentiation. Things can get pretty hairy. But one of the basic techniques we have is integration by parts. It's like one step up from substitution, right? So, no. Integration by substitution. If you really look at what's going on, you'll realize that integration by substitution is sort of the chain rule for integrals. Right? Basically, integration by substitution says if I integrate something like f of u times u prime du, the result is going to be big F of u, right? Fu, right? Right? Where the idea is you substitute some inside function, the derivative must be on the outside, but if you realize this was just the derivative of the, I can write it in more familiar terms. I can write this like f of g of x times g prime of x dx, and notice that this was just that, right? That's basically what substitution is. If you look at it carefully, you'll realize it's just reversing the chain rule, right? Integration by parts, on the other hand, is the reverse of the product rule. This is going to be like a product rule for integrals. This is the guy you're going to use when you're doing a product of functions. You get integration by parts. Let me show you how it works. If I do f of x times g of x, and I'm taking the derivative, what does that give me? F prime of g plus fg prime. Right? Now, what if I try to undo what I just did? I can take the derivative of both sides. Derivative of f times g prime equals the antiderivative of f prime of g plus the antiderivative of fg prime. So now what can I say? Well, if I anti-differentiate a derivative, what happens? Fundamental theorem of calculus says they just kill each other, right? So this side just becomes f times g again. And this side, I can say, I can pick one of these guys. This is fg prime plus the integral of f prime g. And what you basically do is you solve for one of these guys. So I can solve for the integral of f times g prime. That would give me f times g minus the integral of f prime g. This is basically a formula for the integration by parts. You just reverse the product rule. The book would use different notation, so I'll introduce that. So if we set something like, I call f of x equals the function u, and I call g of x equals the function v, which means f prime of x, I think of it as the derivative of u, they just refer to it as du. G prime, I can call the derivative of v. Then the formula becomes the integral of u dv is equal to u times v minus the integral of v du. This is called the integration by parts formula. Memorize it. It's just something you know now. I'm going to test you on it. I'm going to put it on quizzes and all that, so just memorize it. It's just, we know this now, okay? All right. That's a formula. So, idea, given a product, it may work out to choose one function to be u, the other to be dv, and then you can integrate the product. With the above formula. So I'm going to give you the steps, and I'm going to tell you how to actually choose these functions, but let's actually jump into an example so you can sort of see how it works. And then next time, we'll actually cover this in detail again and do some more examples. So not to kill ourselves, we're going to do a very simple example. The antiderivative of x times e to the x. Take a second to appreciate, substitution will not work here. The power rule will not work. No rules that we have so far will work for this integral. This will work. What is the trick? Here, I'm going to choose u equals, I would choose u equals x. I will choose my dv to be the other function, e to the x dx, right? So I call this my u, that my dv, right? So now I have this side. If this is my u, then what's my du? 1 dx. If this is my dv, what's my v? I anti-differentiate, right? So that's just e to the x. This means that the integral of x e to the x dx is u times v, right? So I'm going to take x e to the x, this is just my u times the v, minus the integral of v times du, right? So it's going to be e to the x times 1 dx, right? This is the v times du. This is x e to the x minus, what's the antiderivative of e to the x? E to the x plus c. That's the antiderivative of x e to the x. So the antiderivative of x e to the x dx is equal to x e to the x minus e to the x plus c. It's not something you have to have memorized. I'm just highlighting them. Yes?
I have a question. Say your v is not e to the x, say it's like something else, and like, is it possible that you would have to integrate again to go over the whole process again, like how we did
Yeah, the process can get pretty involved. This is a very simple example just to get have your heads wrap around the idea. I also want you to appreciate, had I chose things differently, what if I chose my u to be e to the x and my dv was x? What would have happened? My du would have been e to the x. What would my v have been? X squared over 2. So now when I take v times du, I would have x squared over 2 times e to the x. So I would have gone from trying to integrate x times e to the x to now integrating x squared times e to the x. I would have actually made the situation worse for myself. Being able to choose wisely who gets to be who is going to be a very important element of this process. Next time I'll tell you how to choose it.
If you switch there around, do you still get the answer that the same answer?
What do you mean?
Like you said,
If I choose u to be e to the x?
yeah. Basically,
No, I wouldn't get anywhere. I would get worse. Right? So there's a method to the madness of what to choose here. Next time I'll tell you how you choose, and we'll do some more examples. We'll stop there.